In this section, we're going to look at radicals and alternate ways we can express those radicals and how they are related to rational exponents. Whenever we say the word rational in mathematics, generally what we're talking about is the rational number set, and this includes fractions. And so generally when we're saying rational exponents, we're talking about numbers that can be expressed in a fractional way, a over b, where a and b are real numbers. When we do talk about radicals, we're basically talking about something or an operation that we have that can undo powers. And generally we're kind of introduced to that idea with square roots. So a radical or a cube root or square root or any kind of root is a way for us to undo a power. So it's, in a sense, it's an opposite operation on a power. And we kind of define this idea of a square root that if the square root of a is equal to some number b, so we take the square root of a number, say 25, and we get 5, then that number squared will also equal a before it's square rooted. So 5 squared would equal 25, and b would be a positive number. The reason why we have to say that is because generally we have the principal square root, which is positive square root, but and we'll talk more about how a negative can play into it, but we always assume if there's not a negative sign there, that we're talking about the principal square root, which is positive. We also cannot take square roots of negative numbers. That's kind of a big no-no. But we'll get to where we do need to take negative square roots into consideration here in a bit. Let's look at some more properties of square roots. First of all, we can say for any real number x, the square root of that value x squared will be equal to the absolute value of x, meaning the positive value of x. First of all, if we square anything, it becomes positive. And then if we're only taking the principal square root, which again, the principal square root is the positive square root, we're always going to get a positive result, because we cannot take the square root of something that's been squared and end up with something negative. Also, if we have a square root of x and we square that, we will get x if x is greater than or equal to 0. So generally when we're dealing with square roots, we usually just deal with the positive or principal square roots. Now, if we're talking about any real number, x, and that number squared is equal to a, then when we talk about the solutions to that equation, where the left-hand side has to equal the right-hand side, we need to take into account the positive and negative square root of a. What I say in general here is that whenever we're solving an equation that involves something that's been squared, there are two possible roots there that we always need to take into consideration. For example, let's say we just took, or we're told that a squared is equal to 4. And so we want to find the solutions, the values of x, that actually make this true. Well, 2, of course, you guys know, squared gives us 4, but that's not the only thing. Negative 2 is also something that if we square it, we get positive 4, right? In a statement that involves a square, we always need to take into account the positive and the negative roots that exist for that. So whenever I take, or whenever you take the square root of both sides of an equation while you're trying to solve it, we always want to take the positive and negative root, because in reality there are two solutions to that particular equation. So if a and b are both greater than or equal to 0 and are real numbers, We also have this property here, which will carry on to the more general. A lot of these are dealing specifically with square roots here, and if we don't have a different index written there, we assume it's a square root. So if we have a number that is a product, we can break it up into two separate, smaller square roots. A lot of times we're trying to simplify a statement that involves a square root. We want to look for perfect squares that are factors of that product and pull out any perfect squares that we see. And then this also goes in the other direction, where any two, as long as we have square root times a square root, we can find their product and put them all under one square root. So this kind of goes in two ways. It's the multiplication property with square roots, but it's also a way for us to simplify them. And the same is true here. If I have the square root of something divided by the square root of something or something else, we can simply take the square root of the whole thing and deal with the numbers underneath them. And we can also break it up to simplify. So for example, if I have square root of 50 here, I say, well, can I simplify this? And since I know that if I look for any perfect squares that I know go into 50, like 25, I can break this into two statements, 25 and 2, and then go ahead and simplify the part that is a perfect square. And so this would be the more simplified version of the square root of 50. In a similar way, if I have 25 over 64, and we're trying to take the square root of that, well, 64 and 25 don't have any factors in common, right? 5 only has 5 and 5, 1 and 25 that go into it, and 64 has no 5s in it whatsoever. But I can still simplify this by taking the square root of the individual parts of the quotient here, and that does simplify down to 5/8. So in working with radicals, it's important for us to kind of gauge what are the rules that we work with. We've looked at a couple, but we're going to generalize it a little bit more, so we're not just talking about square roots, but we're talking about every type of radical. First, let's just define some of the terminology we use. When we talk about a radical, we're actually talking about the symbol that you're all used to seeing and thinking in terms of it being a square root symbol. Yes, most of the time it is, and we assume it is unless we're otherwise told so by the index, which is the little number here. If the index is anything, well, if there is an index there, it's generally because we want it to not be a square root. If there's no index there, then we assume it's a 2. The index there tells you what type of radical or root that we're taking. If it's a 3, then we say it's a cube root. 4, it's a fourth root, etc. And then the number that's underneath the radical, we call that the radicand. Oops. The radicand, fancy old word there, but there we're just talking about the number of which we wish to take the square root or the cube root or whatever indexed root that we have. Okay, so going down and here we are basically kind of just giving the whole idea of the index and the powers and that they undo each other, right? Raising something to the nth power that you're taking the nth root of simply leaves me back where I started with A. And then we saw this applied to square roots, but that applies to every type of square root or every type of root, whatever our index is showing. And it's two things at once. It's showing us how we can break up a product, right? Something that's being multiplied into parts of products, into factors. And we can separate those and then take the roots of either of them separately from the other. Or it shows us how to interact two radicals as long as they have the same index, and we can go ahead and multiply them and write them under a single radical. Depending on, what our goals are. Sometimes we're wanting to simplify and break them up. Other times we're wanting to put them together under one. And that's true for multiplication and for division. We can divide two radicals as long as they have the same indice. All right. This is really showing us a prioritization and showing that they're both similar. And I just want to maybe give an example here. Let's say that we have the, let's say I'm going to go ahead and do the cube root of 8 squared. Okay, so we want to simplify this, and we're asked to simplify it. The question is, if you look at this and know that 8 is a perfect cube, which it is, 2 times 2 times 2, 2 times 2 is 4, 4 times 2 is 8, so 8 is a perfect cube, can I take the cube root first? And this is basically saying, yeah, you can either think of it like this, where in essence we'd be taking the square first, because we always do powers first, and then we would take the cube root after we've done that. But ultimately we get the same result if we take the cube root first. So we put this into parentheses, which parentheses always emphasize priority. We took the cube root first, and then squared the result, not cubed the result. And yeah, these are the same thing. I can also just square 64 and then take the cube root of 64, but because the cube root of 64 is 16. I'm sorry, not 16, I mean 4. So just if I go this way, right, I take the cube root of 8, that's 2, and then 2 squared is 4. But also, if we square it first, the cube root of 64 is 4. So either way, we end up with the same answer, and that's essentially what is being said here. It's really a matter of prioritization. Do we want to do the power first, right? Raise it to the power and then take the nth root, or should we take the root first and then do the power? So prioritize what's in the parenthesis, take the root, and raise the power. It doesn't really matter. Both come out to be the same thing in the end. Also here, if you have multiple roots going on, and here we're taking the mth root of the nth root of a, then we can take the root of the product of m and n. And that will, that's something that can help us simplify more complicated things. Also, when we're taking the nth root of a to the n, this again goes back up to here, and this property tells you that, so basically the power and the index are the same, right? So just like up here, we get absolute value of a. So in other words, it'll always be positive if n is even, but it'll be just whatever a is if n is odd. This is important because when we move out of square roots into cube roots and otherwise odd roots, we actually can have negative outcomes. For example, we see that if I have negative 3 cubed and I'm taking the cube root, just simplifying this out here, negative 3 cubed is negative 27 because you've got that extra negative in there. And then you'd think sometimes that this is not allowed, but the cube root of negative 27 is what number times itself 3 times results in negative 27, and that answer is negative 3. And that's fine. That's true. That's good. So you can see that it was just A, but if we had an even there, so let's say we had negative 2 squared, and we're taking the square root, whenever we square something or raise it to an even power, it becomes positive, and then we're always going to take the positive root there, because we actually cannot take the square root of anything negative. So without getting into a whole nother set of numbers, which we call the imaginary number set. So in looking at simplifying radicands that are under radicals, it's important to be familiar with some of the perfect squares, perfect cubes, perfect fourths that exist. And a lot of us are more familiar with like the perfect squares. We might be somewhat familiar with some of the perfect cubes, but we're rarely ever super familiar with super fourths and super perfect fifths. So it's important that we familiarize ourselves with these. One, of course, is a perfect everything. If I take 1 cubed, it's 1, 1 to the fourth is 1, yada, yada, yada. So let's move on to the next number, that if we raise it to the third power, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and then by the time we get to 5 cubed, we're already at 125. So most of the numbers that are perfect cubes are 1, 2, 3, 4, and 5 are the ones we need to be familiar with. And then we can use our calculators to kind of figure it out. Perfect fourths are a little harder. 1 to the fourth, again, is 1, but 1's not really helpful to us. It doesn't really break a number down. 2 to the fourth is 16. 3 to the fourth, oops, okay. 3 to the fourth, sorry, I erased my 2 there. 3 to the fourth is 81, so we're already starting to get really big. By the time we get to 4 to the fourth, 4 to the fourth power, we're at 256. So, yeah, at any rate, that's super high. And normally we're not going to have a number larger than 256 that we have to break down, right? So, and then when we get to fifths, of course, 1 to the fifth is 1. 2 to the fifth is 32. 3 to the fifth takes us pretty high in and of itself. We're at 243. So, as you can see, yeah. So, there's not a whole lot of numbers that we need to be somewhat familiar with. We can just kind of be familiar with some of the basics. So, as we go to this first example here, where I have the cube root of 135. We know that whenever we have an odd number, we know 2 is out. So I know I don't have to worry about 8 going into this, because 8's even and 135 is not even. But it's possible that this is divisible by 27. And so I'm going to check for that. You also know it's divisible by 5, because 5 is the last number there. And we find that this actually is divisible by 27. 27 times 5 gives us 135. So we can break it down that way, knowing that, and we write this out here, that the cube root of 27 exists. It's 3. And so we were able to pull out a perfect cube from my number. I like to think of it as pulling it out. Then let's go to the fours. I know that 164 could be divisible by 2. So I'm going to see if 16 maybe goes into that. So if I take 164 and divide it by 16, and I'm just pulling over to my calculator, see it's not. Is 164 divisible by 81? it is not. And so we see 164 actually is not a perfect fourth and has no perfect fourths that go into it. 164, it is not divisible by 16, and 16 is the perfect fourth, the first perfect fourth that comes up. But a to the fourth is a perfect fourth, so I would write that as a 164 fourth root. Now, whenever we have generally, and a lot of times this will be written out of the instructions so that you don't have to worry about it, but whenever we have this even root, even index, with an even power, and we get an odd result coming out of it for a variable. So we have this even, odd, like a lot of square roots, for example, when we took the square root of a squared, we have to show that that we're going to take the absolute value of that variable. This is an even though we don't write it, even index, even power, odd outcome. And so in this case, we would want to put that around there unless they tell us to assume all variables are greater than or equal to 0 and represent positive numbers. And technically, to make this true, because from this statement, if I were to plug an odd number in there, not an odd number, a negative, so we have negative 2. Negative 2 to the fourth is going to be positive 16. And then if I took the fourth root of that, it would not give me negative 2. Right? The fourth root of 16 is 2, not negative 2. And so we're trying to make this so that any a can work. So if it's all real numbers, then we need to put absolute values because negative numbers are real numbers. But if we're told that a must be a positive number, then we don't have to worry about the absolute value symbols. So always keep in mind that even, odd output, that's where we have to specify with absolute value symbols that we're only dealing, or the only outcome there will be a positive number. All right, and then for the last one, 32, we're doing the fifth root of that. So the way this is written with the cube underneath there, we would generally raise that first. But it's probably going to be easier in this case to take the fifth root of 32 first, since 32 is a perfect fifth, and then cube that result. Because otherwise 32 to the third power is going to be a pretty big number. And then we're going to have to take the fifth root of something really big that we're not as familiar with, but we can immediately know that we're familiar with 32. So, let's get this down to a smaller number first. The fifth root of 32 is 2, and then 2 to the third is something we can do without a calculator. We know that's 8. All right, so if we can be familiar with these, we can make them simpler so I don't even have to reach for my calculator. But we want to be familiar with the numbers, especially the cubes. These tend to come up a little more often. And, of course, the perfect squares as well, because a lot of times we're dealing with square roots. Remembering that what we were doing when we were simplifying radicals was really the multiplication property of radicals in reverse, which says that if we have the nth root of a times the nth root of b, that this is equal to the nth root of a times b, meaning we can just take the number, as long as we have the same index, we can multiply what's underneath the radical together and put them as one, under one radical. The same is true with the division of 2. The nth root of a divided by the nth root of b is equal to the nth root of the quotient a over b, or a divided by b. So with multiplication and division, we can carry out that operation of multiplication or division as long as we have the same indices, as long as n is the same. With addition and subtraction of radicals, it's a little bit stricter. Two radicals that have the same index and the same radicands, meaning the number underneath that radical is the same. They are quote-unquote like radicals and can be added or subtracted. And by added or subtracted, we're really meaning written as one with a different coefficient number out front. I like to think of it in a similar way with like terms that we're adding together. For example, if I have x squared plus 3 more x squareds, whenever we're changing the coefficient, right, when I write 3x squared is x squared added to itself 3 times. Same variables with the same powers, kind of like the same radicands with the same indices. We can just express them by adding the numbers that are out front. And so if I have one more here, all I'm doing is adding 1 more x squared. This gives me 4 x squareds. Multiplication is just a quicker way of doing multiple additions of the same thing. So these are all the same thing, right? Put any number in for x. X squared would be, if x is 2, that's 2 squared 4. So we're going 4 plus 4 plus 4 plus another 4, right? Another way to write that is 4 times 4. So the number out front is indicating how many things you have being added. And so if the same thing is being added, we can add them together by changing the coefficient out front. Many times if I look at the form that these are in, for example, right here we have square root of 45 and then we have the square root of 20. Not the same radicands, they're both square roots, but I can't add them together while they're in this form. Now the question is, most of the time, if they're giving you this as a problem, it's that this can be simplified. And so we want to think of all the perfect squares that go into 45. And so we can start with, well, wait a minute, okay, let's go with the lowest perfect square besides 1 would be 4, but 4 doesn't go into 45, it goes into 44 11 times. So we go to the next one, which would be 9. Does 9 go into 45? And of course, yes, 9 goes into 45. 9 times 5 is 45. So started with the lowest one, lowest perfect square, which is 4. Then we went to 9. The next one I would try after that would be 16. But if, I would go to 16 and then 25. And then, 5, 6, 36, 7, 49, 8, 64, so on and so forth. Well, of course, none of those go, those high numbers. You only have to go as high as the number itself. So 45 can be written as, or it can be simplified. Square root of 9, square root of 5. 9 times 5 is 45. So 45 can be rewritten as 3 square roots of 5. And then we want to think about 20. Well, 4 goes into 25 times as well. So again, square root of 4, square root of 5. Square root of 4 is 2. Then we have that 2 times 7. So that's going to be 14. And then we have square roots of 5. So we have 3 square roots of 5 plus 14 square roots of 5. That can be simplified simply by writing 17 square roots of 5. Going on to the one that we have here, now I want to think in terms of perfect cubes. Perfect cubes, there's a lot fewer of them. We're just not as familiar with them, but there's fewer of them, so that's one of the good parts. So we'll start with, we'll start with 80 here. I know that x, when I look at the variable underneath here, x itself is not a perfect cube. So that's going to stay underneath the radical. But we start with the first perfect cube, which is 2 cubed 8. And we see that 8 does go into 80 10 times. So that's 5. I'm going to rewrite my cube root. Remember to carry the index with you there. So 8 cube roots of 8, and then we have the cube root of 10x left over. And cube root of 8 is 2. 2 times 5 is 10. So that leaves me with 10 cube roots of 10x. Subtracting, let's see what we can do over here. 8 doesn't go into 270, but the next cube root, 27, does 10 times. So this is subtracting 3 times the cube root of 27 times cube root of 10x. Generally, with these problems, once you've got one of them, you kind of know what you should be left over with if they want this to work. Otherwise, we just won't be able to do anything. And sometimes you might be faced with that. But the cube root of 27 is 3, so that leaves me with 3 times 3, which is 9 cube roots of 10x. So I have 10 cube roots of 10x minus 9 cube roots of 10x. That leaves me with 1 cube root of 10x. So this can simplify down to that, which you'd agree is much simpler the way that we simplified it down there. So with addition and subtraction, we must have the same index as well as the same radicand. With multiplication and division, we only needed the same index. Okay, we're going to talk about another way that the radicals can be sort of viewed, and that's through a fractional or rational exponents. I'm going to go back to one of the rules that we have with exponents. You might remember, maybe you don't. I'm just going to take a cube here. Whenever we had a number that's raised to a power and then we raised it to another power, for example, if I take 2 cubed and I square that, that will give me 2 to the 6th, because 2 to the third squared is 2 to the third times itself. So that tells me I have 6 cubes there. So in other words, we multiply m times n. So if I was taking 2 cubed, for example, and I wanted to just undo my cubing, I want to make it basically 2 to the 1, right? I want to do the opposite operation and just undo what I just did was, whoops, I cubed something and now I want to undo that. We basically want to get it back to its original root there, which is 2. And so you have to think, okay, well, what would I multiply 3 by in order to get 1? And of course, we know that we would need to multiply it by a fraction. 3 times 1/3 is 1. So this gives us an idea of what a fractional exponent is. A fractional exponent, which we would say is rational exponent, is a fractional exponent is a radical, just in a different form. So a to the m over n, m over n being, a fraction, sorry, that's kind of obvious, is equal to the nth root of a to the m power, or a to the m nth rooted. So there's a relationship there. Notice that the number on top is always a power, right? It's being raised to the power, it's being raised to the power. And whenever we put that over something, that's where this is something that's new. That's where we're introducing something, and it is the index of the root that we're using here. So the 8 raised to the second, or to the 2/3 power, is 8 squared and then cube rooted, or cube root of 8 squared. Notice how those are the same operations as what we see up above. This is written that way, this is written that way, but they represent just which order we're going to go in here. This indicates that we're going to take the cube root first, which leaves me with 2, and then we saw 2 squared was 4. Here, this tells you to square first, giving you 64, and then to take the cube root of that, which also is 4. 4 cubed is 64. So whenever we see fractions as exponents, this can be rewritten into radical form and vice versa. We can also just put radicals into fractional exponent form if we wish. They are equivalent to each other. And there are times where one form might be more helpful to us than the other form. Given that radicals can be written in an exponential form, then we know that any radical is going to, or we can manipulate and change, rewrite those radicals in exponential form. And so it's helpful to us to remember the rules that we use when simplifying expressions involving exponents. So going back to the rules involving exponents, we see here that as long as we have a similar base raised to different powers and we're multiplying those, we can put them with one base and then adding the exponents. For example, if we have 2 squared times 2 to the third, thinking about what those represent, 2 squared is 2 times 2, and 2 cubed is 2 times itself 3 times. And then we're multiplying them. Notice everything here is multiplication. I put the parentheses there, but I could remove them because everything there is multiplication. There's literally 5 2's that are being multiplied. And so that's where we add those exponents, which we will probably, because we see that multiplication, want to multiply those exponents, but that's not what we would do correctly. We want to add them up. The sum of my exponents tells me how many 2's, how much of my bases I have being multiplied. Okay, then we can move on, which is kind of a way to remember this. We're doing the opposite, right? Here we're multiplying. Here we're dividing. A fraction is simply a division. And so multiplication and division are opposite operations, and so it's no big surprise when we see that we're going to do the opposite operation on their exponents as opposed to what we did with the product rule. So if I have 2 cubed and divided by 2 squared, for example, keep in mind that 2 cubed is 2 times itself 3 times, and 2 squared is 2 times itself 2 times. And we see that within this fraction we have similar bases. And so those can all cancel out. I'm left with 2 to the 1, which is the same thing that we would get if we go 3 minus 2. In a division, right, powers are representing multiplication, and in a fractional setting, a fraction is a division, which is an opposite operation from multiplication. So we do the opposite operation on the exponents. We subtract them. And that's a simple way for us to simplify. Okay. And then we have the power rule. This is what we looked at previously there. Any base with a power raised to another power means that to simplify that, we would multiply their exponents. Multiply the exponents there. So, like I showed earlier, but I guess it's helpful to show it a second time. If we have 2 squared and I'm cubing that, well, by cubing 2 squared, that means you have 3 2 squares. Lots of 2's here. We have 3 2 to the second powers, which, again, using the product rule now, we would go 2 plus 2 plus 2, which is 6. So, and 2 times 3 gives me 6. So that's just a quicker way for us to get to that 6. And then the very last one that we're not as, maybe not as familiar with or may not remember is what to do when we have a negative exponent. It's 2 to the minus 3 or something to that effect. What does that mean? We can kind of actually look at the progression. For example, if I have 2 cubed positive, that's 8. And then take that down by 1, 2 squared. Well, that's 4. To the first, we're down to 2. So what's happening here is I'm dividing, my result is getting divided by 2 because I have 1 less 2 that I'm multiplying by. And so if we continue to divide by 2, we actually see what 2 to the 0 is, which is another thing. 2 divided by 2 is 1. So that's another rule of exponents. Anything to the 0 power always gives me 1. Notice that if I go 2 divided by 2, I get 1. So what happens when I keep that pattern going? Negative 1. Well, we could assume the same result would happen here. We would divide by 2. Well, 1 divided by 2 is 1/2. Notice how it moved what was in the numerator down to the denominator. And then what if I do it again? I say 2 to the minus 2. Well, that would just divide this by 2 again, which is actually 1/4, which is 1 over 2 squared. So again, what was in the numerator moves to the denominator. 2 to the minus 3 then logically would be 1/8, which is 1 over 2 cubed. So anytime we have something raised to the minus to a negative power, it actually can be re-expressed by moving it to the denominator. Once it moves, that base moves down there, that power becomes positive again. And if it's already in the denominator, we can just move it back up to the top. And once you move it, it becomes positive again. This is the negative exponent rule. One of the ways that when I introduce this to my students, I talk about the differences between living in an apartment complex where you live on the second floor or live on the first floor. Well, of course, we always want something that's different than what we have, but there's always negatives about living on the first floor or the second floor in an apartment. On the second floor, you got to deal with all the stairs. On the first floor, you're going to hear all the noise from people above you, right? So if you're a landlord, the negative kind of means they're not happy where they're at, so you move them down to the new place, and then they are happy again. And if they are living in the bottom and they're unhappy, and you say, okay, well, let's move you to the top and make you happy. So the negative, if you think of it as an unhappy tenant and you're the landlord, you kind of can move them around like that. All right, so then given that we have negative and fractional exponents, let's look at ways using the rules of exponents to simplify stuff. So for example, let's start with A here, where I have 4 multiplied by x to the 1/2, which would be the square root of x, times 3 times x to the 1/5. Notice that I rewrote it, not because you have to do it this way, but I just wanted to emphasize we see the numbers right next to the variable there. We think that they're really connected in some non-disconnectable way. But everything here is being multiplied, and when everything here is being multiplied, we actually can just kind of disconnect them and multiply the things that actually can be multiplied, like 4 times 3 can be multiplied. X to the 1/2 and x to the 1/5 can also be multiplied. We just have to add their exponents according to the product rule. So really what I want to do is take 1/2 and multiply or add it to 1/5. And so we've got to have common denominators there. We need to rewrite these so they have a common denominator of 10. So if I multiply the top and the bottom of here by 5 and here by 2, we can see that these would come together if we add them to give us 7/10. And so this would give me, or if I combine these together, I get 12 x to the 7/10. And that being the case, if I were to rewrite this in terms of radicals, this would be 12 times the 10th root of x to the 7. Yeah. Now, which one is more presentable? Which one is easier or more simple? They're both pretty not simple. So either one of these are just equivalents. It's kind of like going just from one to the other. They're on equal levels of difficulty, so one is not necessarily more simple than another. They're both equally as simple or not simple. All right, what about the next one here? We've got some positive and some negative things in a fraction. So how do we deal with this? Let's take a look at it from keeping in mind that what I have in top is a product, right? We don't have to write that there. But sometimes it helps to clarify for us what we have and what we should do with it, or what we can do with it. These are all products, and so I can actually look at the numbers and simplify them right away. Like 5 goes into 25 once, so that got rid of that. I also have these x's, so the same base raised to different powers in a fraction. This one's negative, so one of the other things I could do is to bring that down, move it downstairs there. And that leaves me with the 5 on the top, x to the 1/4 and x to the 1/3, both on the bottom. Same base being multiplied. And so I can add those exponents, 1/4 and 1/3. And we can do that as long as we have the same denominator. So think about a number that both 4 and 3 can go into, 12. That would multiply the top and the bottom here by 3 and the top and the bottom here by 4. And then adding those together, that gives me 7/12. So putting those together, that would be 5 over x to the 7/12. Okay. And we could leave it like that. X cannot be, or x is greater than 0, so we don't have to worry about that per se. And but there's other ways I could have gone about this as well. Right, with the x's on top and bottom, I could use the quotient rule, which when we use the quotient rule, we're assuming something over 1, so we're assuming it's on the top. But this would be negative 1/4 minus 1/3 or plus negative 1/3, which would give me x to the negative 7/12, which would again move it down to the bottom. So we would end up with the same thing eventually. So there isn't necessarily just one way of going about this. Sometimes we could have multiple ways of getting to the same end. All right, let's look at this last one here. And I've got a base with a power raised to a power, and when we have a power to a power, that goes back to the power rule where we can multiply those exponents. So this would be x to the 2/3 times negative 1/5, which is x to the negative 2/15. So it's negative. We think of that as being over 1, so that would move this down to the denominator 1 over x to the 2/15. Now my exponents are positive, and so that can be my final answer. We're going to look at simplifying kind of a complicated expression here. I'm assuming you would agree that this is somewhat complicated. I've got 4/3 x to the 1/3 multiplied by something and then adding. And eventually we want to be able to factor this and simplify it, combine terms that are like, etc. Before I factor it, I'm going to unfactor it. I'm going to distribute this actually and see if there are things that I can add together, which I suspect there are. So as I take 4/3 x to the 1/3, so I'm going to write that out, 4/3 x to the 1/3, and I distribute it or multiply it by 3x, we notice that everything here is being multiplied. So if I take the 3 and multiply it with the 4/3, that's just going to leave me with 4. 4/3 times 3 is just 4. And then this is x to the 1/3 times x to the 1, so that 4/3 and 1 can add together, giving me 4/3. 1 could be written as 3/3. So if we have 1/3 plus 3/3, 3/3 is 1, so that gives me 4/3. Okay, so I distribute it to the first thing, and then we have to take 4/3 x to the 1/3 and multiply it by 1, so that's just going to be minus itself 4/3 x to the 1/3. And then outside we had this, so 3x to the 4/3. Notice that these two terms are like, so I can add those together. So I'm glad I did this. I'm going to simplify this a whole lot just by being able to add these common or these like terms here. Adding them together, we get 7x to the 4/3 minus 4/3 x to the 1/3. Okay, so what do I do now? If I want to factor this, we need to look at what's in common here. And so when we look at powers, for example, we only can go as high as the lower power that we have, as far as them being in common. So when I look for the least common factor, here my step. Now that I'm ready to factor, I want to rewrite this as a factor term. We know it's going to be x to the lowest numbered power, which would be 1/3. Now, as far as the number goes, I would like to be able to take out the fractions, right? I want to take out the 1/3 that's there. And as we divide each of these by 1/3, 7 divided by 1/3 is actually going to leave me. So I'm going to write this out here. 1/3 x to the 1/3. This will leave me with whole numbers inside my parenthesis by taking out that 1/3. 7 divided by 1/3. When we factor, we're dividing, we're unmultiplying, which is dividing, is the same as 7 times the reciprocal, 3/1, so we actually get 21. So that leaves me with 21, and then 4/3 subtracting the 1/3 that I'm taking out leaves me with 1. For the second part here, I'm just left with 4/3 divided by 1/3, which is 4. And I took out the x to the 1/3. So the factored expression here is 1/3 x to the 1/3 times 21x minus 4.